Welcome to this explainer. If you've ever seen a chunk of sodium metal hit water, you already know it's a completely dramatic, volatile, and frankly explosive event. The periodic table's Group 1 and Group 2 metals, that's the alkali and alkaline earth metals, well, they're famous for this kind of sheer, unbridled reactivity. But today, we're not just going to watch the explosions. We're going to uncover the invisible atomic mechanics behind them. We really want to understand exactly how these core concepts work, literally down to the movement of single electrons, to see what actually makes these elements the true engines of reactivity. To do that, here's our roadmap. We've got Section 1, Meet the Reactive Metals. Section 2, The Engine of Reactivity. Section 3, Alkali versus Alkaline Earth. Section 4, Physics of Flame Colors. Section 5, Chemical Reactions in Action. And finally, Section 6, Everyday Metal Compounds. Let's jump right in. Section 1, Meet the Reactive Metals, Groups 1A and 2A. Okay, take a look at the names of our Group 1 alkali metals here. Lithium, sodium, potassium, rubidium, cesium, and francium. When we hear the word metal, we almost always picture something rigid, right? Like tough iron or steel beams. But the reality for these Group 1 elements is just entirely different. Despite being highly electropositive metals with this shiny, silvery white appearance, they are incredibly soft solids. I mean, they're so soft you can literally take a standard kitchen knife and slice right through a solid block of pure sodium or potassium. It's wild. So to figure out why a metal behaves basically like butter, we have to look under the hood at the atomic level. Section 2, the engine of reactivity, the power of electrons. So the crucial point here is a concept called ionization energy. By definition, this is simply the amount of energy required to rip an electron away from an atom. Because alkali metals have a really large atomic size compared to their mass, their outermost electron is sitting super far away from the nucleus. Think of it like cash burning a hole in the atom's pocket. Because the atom's grip on that electron is ridiculously weak, its ionization energy is remarkably low. These atoms are absolutely desperate to spend that electron as fast as they can, and honestly, they'll react with almost anything just to get rid of it. Which naturally leads us to ask, why does this low ionization energy make these metals so unbelievably soft and drop their melting and boiling points so dramatically? Well, this huge atomic size and their sheer eagerness to just let go of electrons results in incredibly weak metallic bonding. The atoms simply aren't clinging to each other with much force at all. It's a really beautiful example of how a microscopic, atomic-level rule completely dictates the macro, physical traits that you can actually see and touch. And this intense drive to shed electrons applies to our Group 2 metals as well. Alkaline earth metals are strong reducing agents. Being highly electropositive basically means their whole chemical identity revolves around giving away their electrons. By forcing other elements to take their electrons, they reduce those other elements. They're essentially the ultimate chemical donors of the periodic table. Section 3, Alkali versus Alkaline Earth, a tale of two families. Let's compare these two side by side, because it's fascinating to see how just one single extra electron changes the entire game. On the left, our alkali metals form unipositive or +1 ions. They have larger radii, and they are so light that lithium, for instance, has a density of just over 0.5 gram per cubic centimeter. But look over at the alkaline earth metals on the right. They form bivalent or +2 ions. Because their nucleus has an increased nuclear charge, meaning more protons, it literally acts like a stronger magnet, pulling the entire electron cloud tighter. This smaller atomic radius means the atoms can pack much closer together, which directly gives them a higher density, higher melting points, and higher boiling points than their alkali neighbors. Just taking one step to the right on the periodic table tightens the whole system up. Section 4, Physics of Flame Colors, the Mechanics of Light. Now, this electron behavior doesn't just mess with density and melting points. It's responsible for one of chemistry's coolest visual tricks. The exact mechanics of a flame test is basically a three-step dance. Step 1. When the metal hits a flame, its loose electrons absorb that invisible thermal energy. Step 2. This absorbed energy physically excites the electrons, forcing them to jump up into higher, unstable energy levels. And Step 3. What goes up must come down. When these electrons fall back down to their original ground state, they have to dump that excess energy. They release it as radiation, specifically characteristic colors right in the visible light spectrum. And the precise distance that the electron falls dictates the exact color of light we see. It maps perfectly to specific elements. Calcium gives off this striking brick red. Strontium burns a deep crimson.
barium shines an apple color, and radium creates ceramine red. It is worth noting, though, that chlorides of alkaline earth metals produce these colors with two notable exceptions, beryllium and magnesium. Their electrons are actually held just a little bit too tightly to perform this specific visible light trick in a standard flame.
Section 5, Chemical Reactions in Action, Acrobatics of the Elements. So now that we know how their electrons work, let's look at the explosive acrobatics that happen when they meet the real world. What happens when our Group 1 alkali metals are exposed to moist air? Well, they react so rapidly to form oxides, hydroxides, and carbonate layers that they tarnish almost instantly. Because they are so incredibly volatile, sodium literally has to be locked away and submerged under kerosene just to keep it safe from the air. And when they touch water, forget about it. The reaction is relentless. They instantly form metal hydroxides, liberate hydrogen gas, and dump a massive amount of heat, which is exactly why that hydrogen gas often violently catches fire. They even react with ammonia to form metal amides, again kicking out hydrogen gas. Their drive to react is just completely uncompromising. Now, contrast this slightly with our Group 2 alkaline earth metals. They're still highly reactive, for sure, but they're slightly more stable. For example, magnesium burns with nitrogen to form nitrides. When alkaline earth metals react with dilute acids, like magnesium mixing with hydrochloric acid, they happily bubble off hydrogen gas. But check out their action with water. While the heavier elements in this group react pretty easily, beryllium doesn't react with water at all, and magnesium only reacts if you heat it up first. That tighter nuclear grip we talked about earlier, it translates directly into this slightly more subdued chemical behavior. Section 6, Everyday Metal Compounds, from Lab to Life. So what happens after the smoke clears? It's kind of amazing to see the transformation of these wild, unstable elements into absolutely essential, boringly stable industrial building blocks. Take sodium carbonate decahydrate. That's commonly known as washing soda. It's crucial for making soap, glass, paper, and even softening water. Then you've got calcium oxide, or quicklime, which we get by heating limestone. That is the backbone of cement, glass manufacturing, and it acts as a basic flux in metallurgy to pull out acidic impurities. And bleaching powder, which is made by the action of chlorine on dry, sleeked lime, is used all over the world in paper manufacturing and as a heavy-duty oxidizing agent. Which brings us to one final pretty provocative thought to wrap this all up. How do these violently reactive, incredibly dangerous elements, I mean, we're talking about metals that have to be hidden under kerosene or that literally tear water apart on contact, how do they end up being entirely essential to basic human survival and modern industry? Well, it's the beautiful paradox of chemistry. The very instability that makes them so dangerous is the exact same engine of reactivity that we harness to build our stable world. By giving away their electrons so eagerly, they lock into the incredibly strong, permanent bonds that make up the concrete we walk on and the glass we look through. Once you understand the atomic rules of the game, it really changes how you see the whole world around you. Keep questioning, keep learning, and thanks so much for exploring this with me today.